In section 2.2, we relaxed the conditions that we were using in section 2.1 a bit so that we can state and prove some more interesting statements. One thing you'll notice is that in section 2.1, we defined divisibility by specific numbers, but we never just sort of put all of those statements together in one. And so we start off with the definition of A being divisible by D in general. And in that case, we would say that A is some quotient, so we'll call quotient K, times D for some integer K. I'll just write it that way to fit in the blank. So for some integer K, A is K times D. That's exactly what we said when we said that A was even. That meant divisible by 2. On the worksheet in class, we used the definition of divisible by, we've used divisible by 4, divisible by 5, and divisible by 10 in different places, but they always had the same form. So this is what would happen all the time. Just to avoid unpleasantries and inconsistencies, we will require, when we say this, you'll usually see a requirement that D is not equal to 0. We don't want to really get into the issue of dividing by 0. We know that that's not a good thing. So when we write this, generally we will, if we use a general letter like this, we'll have the condition that that thing we're dividing by is not 0. Unfortunately, like many things in math, people don't always talk the same way, and so this idea of divisibility, I can think of two other ways people use this in English. So I just wanted to make sure those were clear before we went on. And then the problems throughout the course, you'll see the terminology kind of dance around to make sure that it's clear to you that they're all the same thing. So for example, if I said 63 is divisible by 7, that does fit my definition. That just means 63 is 7 times K for some K. And in this case, I know that's true because I can just say, well, K is 9, right? K equals 9 would do that. You might see 164 as a multiple of 2. And so if you wanted to demonstrate that, you would say it's because 164 is 2 times something. I'll use a different letter here for some integer Q. But notice that's exactly the same thing as if I had said 164 is divisible by 2. So being a multiple of 2, if I could write divisible by 2, words running together. So being a multiple of 2 and being divisible by 2 mean exactly the same thing. And then perhaps less common is this terminology here that 4 divides 12. So again, what we think of when we see 4 divides evenly into 12 is that 12 is divisible by 4. So again, we would say that's because 12 is 4 times some integer. And that means exactly the same thing as 12 is divisible by. I keep saying the word by while I'm writing that down, so I want it to say, no, anyway, doesn't matter, divisible by 4. And so those two, the difference between divides and divisible by is sort of active versus passive voice, but there's a grammatical thing going on there, but all these ways are saying divisible are the same. Just a quick note, note that 0 is divisible by anything. It's not interesting, but if you do 0 divided by something, you get a whole number. So that is true because 0 is definitely 37 times something. I'll go back to K for some K. So it fits that definition just right, just fine. In this case, the K would be 0. And so people do sometimes confuse the fact that you can divide 0 by anything, but you can't divide by 0. So it does matter which way around it is. All right, so let's just see an example similar to the ones we did before, but using a different number than we've used before. So for divisibility by 7, if we have a hypothesis, if m and n is divisible by 7, then I want to conclude that this combination of n and m is also divisible by 7. So I start off by inviting the reader to pick an example satisfying the hypothesis. So my first sentence matches the hypothesis exactly, so there's no question that that's what I'm inviting the reader to do. My second sentence here is to explain what the definition tells us about the first sentence. And of course the definition is just right up there at the top of the page if you think about D being 7. And then you see my hints, which is usually my cue that I am turning my attention to the conclusion. And the conclusion is talking about 3n plus 2m. And so I want to start with that. And so I ask myself, what do I know about those? And the answer is not much, but I do know that n is 7k, and I do know that m is 7l. So I can just substitute for the n and the m based on the one thing I do know. And then I would remind myself what it is well, maybe I do one more step. I'll just do the algebra that kind of pushes all this, gets rid of my parentheses so I can kind of see what I have. So that's my expression without parentheses, so I have an idea of what I'm looking at. And then I just remind myself what I'm trying to do here. I'm trying to show that that's divisible by 7, which means I want to show that this is 7 times a whole number. And so I can algebraically factor out a 7, and then since that thing in parentheses is a whole number, then that's my definition of divisible by 7. I've shown that 3n plus 2m is equal to 7 times an integer. And then once again, this being an integer is really the essential thing, right? Everything is 7 times something, but only multiples of 7 are 7 times whole numbers. So that's why this gets a point of emphasis in our proof. So one of the main reasons for putting this in a more abstract form is because you'll notice that you will get tired of writing the same proofs over and over again when they're just using sort of things you think of as basic facts about divisibility and multiples. When we do want to prove things as general facts, then we can still do it using exactly the same process, but it feels more abstract because there's just more letters running around. So for example, if I wanted to show that adding together two multiples of d gives us a new multiple of d, that's a nice general statement that would apply to anything. If I add together two evens, I get an even. Two multiples of 3, I get another multiple of 3. Two multiples of 7, I get a multiple of 7. And so that becomes a nice general fact, and that's what we'd like to, just where you want to sort of get to when you're studying mathematics or sort of the general properties of things. But notice how many letters there are in this. There are no numbers to pin myself to. So I have to take a deep breath and do it the same way I did before, but I just have to use the letters instead of the numbers. So I'd start off, let A and B be given such that I'll just say both are divisible by d, divisible. I'm having a terrible time with that phrase, divisible by d. And you'll notice here that as soon as that becomes a letter, I'm just adding the condition d is not 0 because I don't want to get into that. Are both divisible by d. And so I'm using as my cue there the exact statement of the hypothesis. Right? So the exact statement of the hypothesis is what I'm asking the reader to give me. My second part here will be to say what I know about that. We know that means that A is a multiple of D. So if I write it the same way I did above, you remember up here, in the definition I wrote A equals K times D. So I'm going to write exactly that same thing here. So A equals K times D, and B equals L times D. Gives a different letter, for some integers K and L. So that's what it means for A and B to be divisible by D. Now I'm going to turn my attention to the conclusion, so hence, and the conclusion is here. So the conclusion is talking about A plus B. So I start off with A plus B equals, so it's very clear that I've now turned my attention to the conclusion. I know that A is K times D and B is L times D, so I do know that. I can see that algebraically a D can be factored out, and the reason that makes sense to do is because I'm trying to conclude here that I have a multiple of D. So since the stuff in parentheses is an integer, this shows that A plus B is divisible by D. I can fit all that on here. Draw my nice black box to show that I'm done. That's my proof writing, ta-da. So that's how that looks in a more abstract setting. I think you'll agree that it seems a lot more abstract with all the letters in it and no numbers to go on, but I hope also you see that it really does follow the same four-step process that we've been talking about for our other direct proofs.